Hi, everybody, and welcome back. So we are in the lesson talking about an overview of data science, and we had just given kind of this theoretical discussion, the high-level overview of data science, talking about how one of the pillars is statistics, one of the pillars is computation, and another of the pillars is domain science or domain expertise, and how, as public health students, your domain expertise is coming from your other health classes in the public health context, and your statistical expertise is coming from the other statistics classes. But this is not really a statistics class. This is more a class on computation. And so we're filling out this third pillar of data science. So I want to get into the different components of data science, and this is pulling primarily from a Donahoe paper. And I do recommend that you read or at least skim this paper. It's a little bit long. It could take you maybe an hour or two to read this paper. Honestly, maybe have ChatGPT just summarize it for you. But this is a totally new world where students can just like dump an entire paper into ChatGPT and say, "Hey, give me a summary of this," and it's actually a good summary. That said, I would still like it. I would still read some of the paper in earnest, like just actually read this paper because it is pretty good. I'm going to give you a brief overview of these six divisions that are highlighted in the Donahoe paper. And the first is data preparation and exploration. And so we have an example here. So we're talking about designing the questions of a patient survey, creating a database to hold clinical trials data. And this is the whole point of this is, can we structure our data in a way before we start collecting it that is going to prevent problems coming down the road? There's an old saying, I believe it was Benjamin Franklin, an ounce of prevention is worth a pound of cure, and or a pound of medicine, if you will. And so the idea here is, if you can do a good job with how you collect the data at the beginning, if you do a good job making sure that you're collecting the right data, then you're going to prevent problems from happening down the road. And I can give you an example of this. I will not name the project, but there is a project at a university that I was working with where they were collecting data on they wanted to study like the health and relationship between parents and children in terms of like how their musculoskeletal system was developing. And they had data that they had collected on the parents' heights and weights and data on the children's heights and weights. And they want to kind of relate those two. They're like, okay, well, if the parent is this tall and we have their biological children at certain ages, we're expecting those children to be on a particular growth trajectory based on their parents' genetics and so forth. So is their nutrition related to whether or not they're above or below that growth trajectory, so forth, and so on. So it's a good question. It's a great question. But when they collected the data, they allowed people to input their own heights as like free text. And so normally that doesn't sound like it would be a bad idea, except for the issue that some people would put in their heights in meters and they would say 1.6 m, or they would say height in centimeters, 165 cm. Some of them would put in their height in feet and inches and they would just say 5 space 5. We're assuming that means 5 feet 5 inches. But what if they say 5.5? Is that mean 5 feet 5 inches, or is that 5.5 feet, which would be 5 feet and 6 inches? Some people would just put in 72 with nothing else. And we're assuming that they're not 72 centimeters tall. We're assuming that's 72 inches, which is 6 feet or whatever. And then some people would put it in as 5 FT space 3IN, So there's all these different ways that people inputted their own data based on the units. And it caused it was just havoc in the data. We had one of the programmers that I was working with. She was a student and she was working on her master's practicum, and she was given this data as part of her master's practicum. And she ended up spending months and months and months cleaning this data, just months and months cleaning this data. And it wasn't even done when she finally finished her practicum hours. And she spent a long time just cleaning data on height and weight. And you think about this database had hundreds of other measurements with hundreds of other participants and samples. And she just ran into this issue simply because the data was not structured appropriately at the beginning. So this is part of the issue. If you can prevent these problems, if you can say, I want clean data from the very beginning, and I want to use a very well-designed REDCap instrument. So REDCap is great for this. If you don't know about REDCap, there will be help at your institution for how you can learn REDCap, and I strongly recommend that you take advantage of that. Some people are still going to use Qualtrics and whatnot, and that's fine. You can, but set up the data capture in a certain way so that you are protecting the integrity of your data at the beginning. Now, there are times where that's not possible and you're dealing with secondary data. In that case, you've got to do data cleaning. There was another project that I was on. So all of this is dealing with structuring your data appropriately. That's what we just talked about in terms of like the height examples. But then there's also data cleaning whenever you're handed data that someone else collected and they didn't structure it appropriately, and you want to be able to clean that data in a way that it could stand up to an audit. So many times we work for the national grants for the National Institutes of Health, or we have to submit data to the Food and Drug Administration for clinical trials. And if they audit our process to make sure that we're coming up with the right conclusions, we want to have bulletproof evidence of what we did to fix the data, who did it, when we did it, and why we did it. And the only way that you're going to have a full documentation of that is if you use very extensive computer code. If you've got data in an Excel spreadsheet and you get a phone call from the principal investigator or from the main clinician saying, hey, this data point for this person is wrong. It's actually they're not 5'3", they're actually 5'6" tall. You need to fix that. If your data is just living in an Excel spreadsheet, then you go in and you change it from 5'3" to 5'6". There's hardly any record of who made that change, when you made that change. I mean, there might be a record of when you made the change if you saved the file before and after with different file names, then maybe there's a date. But why did you make that change? What is the justification for it? There's no note field in Microsoft Excel that says, hey, I got a call from Professor Dr. So-and-so that they're in the clinic right now, and this person is not 5'3", they're actually 5'6" tall. And so if you get audited for that, the FDA or the NIH says, well, hold on, this data point got changed. It was originally 5'3". On paper, they wrote 5'3", but your data point says 5'6". Where is the justification for this change? You are fabricating data. You want to avoid that. You want to make sure that your justifications for the decisions that you make in the data are bulletproof. So that's data preparation and exploration. One of the other, so there's 6 total. So that's number 1. Number 2, and these are not in order, but number 2, data representation and transformation. So this is all about how do we actually pull data out of a database and turn it into something that we can work with. A lot of times from the statistical perspective, we just take for granted that we can even import the data into Stata or Excel or SAS or whatever. If the data is in an electronic medical record system, or if the data is in REDCap, there's not a button, like there's not just a quick, simple, like go into SAS, get this data out of the EMR. Sometimes you could build an API to do that, an application program interface to do that, but somebody has to do that, and many places do not have just direct API access. For number one, that's a huge security risk, big HIPAA concerns, all sorts of stuff. But a lot of times, whenever you're learning statistics, you're learning to deal with very, very clean data that's in a CSV file or in an Excel file or just numbers on a table or something like that. So the idea of retrieving data and transforming data from these huge databases into something that looks like rows and columns that you can actually do statistics with, very, very important. So the point number 3 of data science is computing with data. And this is huge amount of what we're going to be learning a lot of all of this stuff in this class. But the word computing should already be ringing bells to say, oh, okay, we're definitely learning some computing in this class. So how do you write instructions for your computer to do what you need to do? Technically speaking, everything that we've done up to this point, you can hire an army of 5,000 graduate students and they will eventually get it done. Um, but we don't want to do that. Number one, hiring graduate students, that's expensive. Number two, graduate students make mistakes. Number three, that's not replicable. That's not reproducible. And we'll talk more about that later, maybe in the next video. But we want to make sure that what we're doing with this data is reproducible, and we have a computational record of what we did and why. Again, this is related to this idea of computing with data, and we have computing languages to help with that. R is one such computing language. SAS is another computing language that many of you might be familiar with, especially if you're coming from public health context, because many public health departments use SAS, different county public health departments around the country use a lot of SAS. And that's fine. That's totally fine. I recommend that you learn SAS as well, especially as public health practitioners. I personally don't use SAS a lot. There are a few times where I still have to use SAS, but most of the time I can do what I need to do in other programming languages like R or Python or Julia or, God forbid, even Fortran or C or something like that. And so this idea of computing with data is that there are programming languages that you can learn to interact with to compute with data. Now, this is the part. So point number 4 of data science, this is the actual traditional statistics stuff. This is where the t-test stuff comes in. This is ANOVA. This is regression. This is Poisson regression, negative binomial. This is, your factor analysis. All this other sort of stuff. This all fits squarely under the data monitoring point. And remember, we were talking about these 6 points of data science. This is the stuff that's actually covered in the traditional statistics class and biostatistics classes. So again, because you've already had a couple of semesters of statistics, either in undergrad or in grad school, and even if you haven't had a couple of semesters of statistics in your graduate program yet, you will eventually, through the course of this program, be it a master's or a PhD, you will eventually take more statistical methodology courses because you need to. You need to understand the mathematics of making good decisions with data. So I'm not going to belabor this point too much, but the data modeling, this is the traditional area of statistics. A less traditional area of statistics, but still important, so this is point number 5, data visualization and presentation. So there are, and this kind of gets more into the psychology side. So I know a lot of computational psychologists and quantitative psychologists that work in this area to make sure that when you visualize data, when you put up a bar chart, when you put up a line graph, when you put up some figure that displays data, that people are able to understand what's going on from that figure, that the figure is accurately and adequately representing the message that the author intended to convey. There's some really great material by a professor at the University of Miami, Alberto Cairo, and his book is, I believe it's called How Charts Lie, or something along those lines. It's all about how people can either actively, like on purpose, or passively, just by accident, make their charts lie, make the figures that they use to display the data tell falsehoods about the data, or hide and obfuscate important pieces of information about the data. So it's very important to get the data visualization right. This comes up some in traditional statistics departments, that you'll have like a data visualization. You might have a data visualization course. From my experience, this often comes up in I've seen it in schools of communication, or someone will teach like a quantitative communication course where they have to learn how to actually make visuals. But oftentimes it will show up in psychology, where people will study how to accurately represent data and the psychology of looking at the image to make sure that the person looking at the image is interpreting the right message. And this is something that I heard years and years ago that stuck with me. It was one of my professors, but I cannot remember who. This is probably 15, 20 years ago. A picture is worth 1,000 words. That's everybody says, oh, a picture is worth 1,000 words. But a picture is worth 1,000 words. Make sure your picture says the right 1,000 words. So use these data visualizations and representations to your advantage to help your audience understand the results and understand the data that you're trying to communicate to them. And then finally, point number 6 of the components of data science is science about data science. We're not really going to talk about we're not going to talk about this that much in this course, because this is sort of an introduction, as I said earlier, introduction to the introduction to data science. This is not a course about the meta of data science. So we're not going to be learning about how to teach data science or, stuff like that. But there are very, very interesting ways that data science has been employed. And then the question of, is data science employed is it employed usefully? And then, so that's a question of utility. If you're not familiar with the idea of utility, that's a concept sometimes from economics, sometimes from philosophy. And then there's another question of, is data science employed ethically? And that is to say, are the tools in data science used for the good of humanity, used to do the right things? And those are questions, and I would say it's less about the science of data science, but the science of data science is meta-analyses of how data science is used. And is it effective? Is it ethical? Is it good? Is it beneficial to science? But there's also some of the conversations here about the philosophy of data science, of what parts of areas that are traditionally called computer science are actually data science, or what part of areas that are traditionally called communication arts are actually data science. What part of areas of statistics are actually data science? And many people would argue that everything in statistics is actually data science. What parts of psychology are actually data science? And so that I said we're not going to get so much into this area this over the semester, but I want you to be aware that it is there. So to recap, we've talked about the 6 components of data science. Just in broad strokes, we're talking about data preparation and exploration, and make sure that data is prepared in a form that could eventually be used by someone, that we're avoiding the idea of garbage in, garbage out. Data representation and transformation, and that is if we have data safely and securely and correctly stored somewhere in a computer, can we get access to it? Can we actually pull that data out and use it for something? And that and the computing with data is, how do we pull that data out? How do we compute? How do we run models? What is the computer languages that we're using for all of this stuff? Data modeling, this is the traditional statistics approaches of, okay, now that we have the data prepared, the data was in an electronic medical record system. We used some computers to get access, some computer code to get access to that data. It is now on our machine, and it is clean, it is tidy, and it's in. So I've got 2 columns. There's the treatment and the treatment indicator, and then there's the outcome, and let's do a t-test. That's the data modeling type thing. And then data visualization and presentation, that's let's present our results graphically or through figures. And then the science about data science, which is, as I said, we're not going to be covering so much. So thank you for sticking with me for a few more minutes here. And I know this video was a little bit longer. Next video, we're going to talk a bit about what is reproducibility and replicability, and then run some basic computer code. So thank you very much for your attention, and I'll see you next time.